All right, last lecture of the unit. We're going to figure out our final way to determine delta H. It's a super easy way. I'm only going to do a couple of examples, so it's really important you guys do your homework. Looking at today's quiz, not thinking homework's getting done. So we'll see how you guys do in comparison to third period, but I don't know if I told you all, it's the big threat. Did I tell you the threat? That ultimately, if those test grades don't come up, they were not really good last time, and the average was way lower than historically. And I don't know if it's the iPads, I don't know what the deal is, but ultimately that homework has got to get done. So if I don't see an improvement in this test's overall average, I'm going to start requiring homework like physics, which kind of is not fun. But my responsibility is to make sure you get to practice and learn the material, and if you're not doing it, we'll just have to go there. So let's do it so we don't have to go there. So anyway, Big Mama. This Big Mama right here is an equation that's super important. Everyone's like, why is it Big Mama? It's just an equation. Well, you're going to see later when we get to enthalpy and we get to Gibbs free energy that this can be used in other contexts as well. So it's a very important thermodynamic term, and you're going to be seeing it a lot. So I've already introduced you to her. She's on the board. Big Mama's got her house coat on, her Hawaiian print house coat with her chocolate shake and her rollers in her hair. So what is this? This is yet a different way to find delta H of a reaction. The sigma, algebra 2 you learned, is the sum of the delta H of formations of all the products minus the delta H of formations of all your reactants. Where do you find delta H of formations? On that table, correct. So you can look at a table, and on your table, the units are kilojoules per mole. Okay? So we know that a heat of formation is the formation of what? 1 mole of a substance from its elements, right? Well, because a lot of our equations have coefficients, in addition to just summing the products, we have to multiply both the products and reactants by the coefficient in the balanced equation, because that coefficient represents number of moles. Since the coefficient represents number of moles, we need to multiply it because, again, a heat of formation is only 1 mole produced. So if you have a 2 in front of it, it means there's 2 moles in that reaction, therefore we're going to multiply it by 2. And you'll see how it works. It's not very hard. Okay, so moving on now to an actual practice problem. Calculate the delta H for the following reaction. So there's no calorimetry in info. Can we do calorimetry? No. Can we do stoichiometry? There's nothing to stoich to or from. Can we do the flippy thing? No, there's no equations to flip. So that leaves us with Big Mama. So right now I'm going to pause the video. I want everyone to find the thermodynamic tables and locate on the video. It's really important as you're looking up these values to carefully look up the states of matter, because water liquid and water gas are in the back. Okay? CO2 gas and CO2 liquid can be found, so watch out. So I know before I plug into the equation, I just want you to get used to the charts. We know that this is going to be 0 kilojoules per mole as far as enthalpy goes because it's a free element, and we don't need to form it. It's already formed. So has anyone found ethanol yet? What is it? Negative 277.69. Okay. Has anyone found CO2 gas? Negative. Negative 285.83. And again, these are all in kilojoules per mole. Now, you don't have to write these down separately every time. I'm only doing this since this is your first time using Big Mama, except if you were in pre-AP, you definitely did Big Mama before. So when we're plugging into Big Mama, we have the delta H of the reaction. We start Big Mama with brackets. So we're doing products. Remember, it's final minus initial. It's always that. So products minus reactants is final minus initial. See that? That's why it's the change, the delta. Delta is always final minus initial. So we have products. We're going to take our 2 coefficient, multiply it by, I'm just going to round to 1 decimal here for time's sake. Okay, that's our one product, plus It's the sum of the products, 3 times H2O. Let me be consistent here with my 3 times negative 285.8. That's products minus my reactant. I have 1 ethanol, 1 mole of ethanol. What do I do about that H2O? 3 times 0. So go ahead and solve. All right, so our answer is negative 1,367. Now, our answer is kilojoules per mole. I know it makes sense in your mind. It did in my mind. And it does in a lot of the textbooks that these moles cancel because this is a mole and that's a mole, so why not cancel them? Some textbooks do that, others don't. So what we have to do is refer to what they want on the AP Chemistry exam. What they want is for us to report any delta H, delta S, or delta G as a joule or kilojoule per mole of reaction. Okay? So these moles do cancel, but that overall delta H is the delta H for 1 mole of that entire reaction. Why? Y'all, it was like a big drama. There's this thing called the listserv where teachers get on and battle and talk, and there was complaining, and so that's the rule, and that's what they came up with, so that's what we're going to do. Okay? So if it's an answer asking for delta G, delta H, delta S, you pretty much just be a monkey and say per mole. And if it makes you feel better, write mole of reaction, because we're not talking about these moles here. We're talking about the mole of that entire reaction up top. There's something else. Oh, and that doesn't refer to, what if you use Q equals MCAT? That doesn't refer to just doing Q out of Q equals MCAT. This only refers to enthalpy of a reaction. Okay? All right, let's go ahead and look at number 17. 17 is linked directly to number 16 because it says determine the amount of heat released at a constant pressure when 1 gram of ethanol is combusted in excess oxygen. Isn't that the equation above? Ethanol being combusted in excess oxygen? Looks to me like we're going to do some stoichiometry, but we're going to end up utilizing our answer here because this was the delta H for that reaction. So I'm going to start with my 1 gram given, 1 gram of ethanol. How am I going to convert? Go to what next? Loud. Moles. Good. So for every 1 mole, anyone found out the grams yet? 46.08. Great. Grams cancel. Now, what do I do? Uh-oh. Good. For every 1 mole of ethanol, which is up there, I'm using the stoichiometric ratio in the reaction. What do I have? Negative 1,367 kilojoules. Since this is exothermic, we'd be basically adding a product of this many kilojoules because it's part of the heat's a product. So our stoichiometry will apply to that, or to that, or to that, or to that, all the way across. Okay? So whatever coefficient's in front is how many kilojoules of heat apply to that. So here, 1, here, 1, because we're dealing with the ethanol. So I need an answer. Negative 29.6 kilojoules of heat released. Okay, Big Mama, we have one more Big Mama problem. This is a little bit different. This is very common. I actually kind of like this one. I've seen it on the last couple AP exams where they have it set up like this. We have to look at the phraseology and don't freak out. It says the standard enthalpy of combustion to CO2 and H2O at 25 degrees Celsius of cyclohexane is negative 3,924 kilojoules per mole. Now, one thing about this, I don't want you to freak. I want you to put a parentheses from 2 degrees Celsius. kind of ignore that because we know when we combust cyclohexane what we get, right? So just read it. The standard enthalpy of combustion of cyclohexane is -3924. What does that mean? What does it mean to be a standard enthalpy of combustion? It's the amount of heat that's released when enthalpy is combusted. Not enthalpy, when cyclohexane is combusted. Isn't that this equation? Okay. So what is that delta H? That's the delta H that goes with this equation. So -3924 kilojoules is given off when a mole of that goes. Calculate the standard heat of formation of cyclohexane. That's this guy. Any ideas? I'm going to let you think. I'm going to pause and let you think. Record all that. All right, so you're going to use Big Mama. You're going to set Big Mama equal to this because that's the heat of that reaction. And you're going to plug everything in you can except for the cyclohexane, which will be the variable x. Now, I had one student last period say, well, heat of formation, can't you just look on the table? Yeah, you could, but look at your table. Can you find C6H12 on your table? I did that on purpose. Somewhere there's a table that has C6H12 on it where you could look at the table, take it off, and say, hey, that's the heat of formation. But the problem specifically says to calculate using this information. So now we're going to set up Big Mama. You still need your table, though, because we need to find the enthalpy of these guys. So delta H, we know, of combustion. The delta H of combustion of this particular reaction is -3924 kilojoules per mole. That is equal to products. CO2, what was it we had at last problem? 0.5, is that good enough? All right, products plus H2O liquid -285.83. Again, we got that from the tables. So those are our products minus our reactant of 1 times, we don't know the heat of formation of cyclohexane, plus 9 times 0. Okay, let's go ahead and solve. 151. Can I get a second on that? Yeah? Okay, so this whole substituting as x is pretty important. Okay, last thing before I let you off on your quiz time is the use of a new equation, and we're going to kind of derive it. You can look at this, but I think it's confusing. I'm just going to show you where this is all coming from. Okay, so this equation that we're looking at is going to relate delta E and delta H along with some interesting things about moles of gases. So let's first start with what you learned a few days ago about the equation for internal energy. What is it equal to? Q plus W. Now, the last couple of days, we've learned that there's a different name for Q. What do we call it? Delta H, right? So I'm just going to change that. Internal energy is equal to enthalpy plus W. Now, you learned, not in physics, I know you got force on the brain from physics, and work is something totally different. But what is work in chemistry? Negative P delta V. So I'm going to replace that in for that, and I get delta E is equal to delta H minus P delta V. All I did was put in negative P delta V for W. You with me? Okay, now I'm going to kind of do a sidestep here, and I'm going to talk about good old ideal gas law. PV equals nRT. Look what we have in the equation. We have P delta V. So instead of just pressure times volume, we're multiplying a pressure times a change in volume. Okay? So if I want to put a delta here, do you agree that if I change the volume I probably need to have keeping this constant, I probably need to have a change in the number of moles of gas. You okay with that, conceptually? Huh, looky there. So now all I'm going to do is replace your negative P delta V with delta nRT. And there's the equation that we're going to be using. Here they have the same equation, but whoever arranged it on this side didn't like the negative sign, so they just swapped those two terms. And this is a way to find delta H, so they're isolating delta H. So that's why this equation is probably the one you're going to want to use. But you see how they're the same? It's just a sign difference. Okay, so let's talk about the variables in this before we work this problem. We know delta H is going to be our good old friend enthalpy. Delta E, and this is kilojoules per mole. Delta E is our good old friend energy in joules. Okay. R, because we're dealing with energy, is going to be which one? 8.31 joules per mole K. And then our temperature is going to be in Kelvin. So what is this new and improved or new and scary little delta N? Delta means what? So this is the change in moles. We are obviously dealing with something that changes volume. That's what this is based on. And this is called the ideal what law? Gas law. So the only thing we're concerning ourselves with is the change in the moles of gases. So for delta N, all you need to do is find the number of product moles of gas minus the number of reactant moles of gas. Sounds scarier than it is, because guess what we're going to use for moles of gas? The coefficients in the balanced equation. That's it. And I'm going to show you how to do this problem. You're going to be surprised how easy it is. Coefficients. Don't freak out. All right, let's look at this. It says the enthalpy change accompanying the formation of 1 mole of NH3 from its elements is that many kilojoules. So what do you think our first step needs to be? Balanced equation. Perfect. We are forming 1 mole of NH3. This is a formation equation. So we have, what two elements make that up? Nitrogen and hydrogen. But we need to balance this puppy. We can't change this one. That's what formation is defined as. So how many nitrogens do we have? 1/2. And how many hydrogens? 3/2. Good. Y'all are on the ball. So again, the enthalpy associated with this equation is negative 41.6 kilojoules. That's all we need, because now we're going to start to plug and chug into our new fancy equation here. So delta H is, I see a problem though with kilojoules. What's my problem? Why do we need it to be in joules? Because of the R. So I'm going to go ahead right now, and when I plug that delta H into this equation here, I'm going to go ahead straight up put it in kilojoules. Negative 41,600 joules. Change it. Okay? Is equal to, I'm solving for the internal energy, plus, now let's look at this delta N. How many moles, and these are, I didn't say it, but these are all gases, because it tells you ammonia is a gas, and you already know that at 298, at room temperature, that nitrogen and hydrogen are gases. So, knowing that, how many moles of gases do we have in products? 1 minus, what's the sum of these two? 4/2 is 2. That's your N. Okay. Times the R of 8.31 joules per mole. Then times your T, I don't know why I'm on this color festival here, 298. So let's go ahead and check our units. We know that this is moles. I should probably write it down. This is moles. So our moles cancel here. The Kelvin, this is Kelvin, right? Our Kelvin cancel, leaving us with joules. Yay! And joules add to joules. Subtract from joules. So let's go ahead and solve. Oh, is it going? Okay. Woo! Save the day. Got really nervous there. Okay. So, Chris, tell me one more time.
Negative 39,000.
Negative 39,100 joules, but we're not looking for a delta H, right? So we're just going to leave it as joules. Do you all agree with that number? I'm hearing some dissension. Yes. Okay, so this is as hard as those get, but let me tell you a secret of how this will be most often used. You will have a problem like this probably in the multiple choice, maybe on the test, but the trick that I'm going to give you is always check your delta N first. Because what happens if I have a delta N where I have the same number of moles of gas on each side? What's physically happening? No work's being done, right? So there really is no change in any internal energy or any heat. There's no differential. So if my delta N ends up being 0, let's look. If my delta N is 0, what happens to this whole term? Goes away. So your internal energy and your enthalpy are the same. That's usually what they do on the AP. They throw you this scary thing to freak you out, and then they're like, oh, there's no change, cancels out, delta H equals delta E. So always check your change in moles of gas first. And we will be revisiting the change in moles of gas at a later date with another equation. So it's something you'll see again in a different format. All right, that's thermo. Yay. All right.